Good morning, everybody. Really appreciate everybody coming out this morning. My name is Austin Shellnut, and I'm with a company called Strategic Thermal Labs. And I'm joined up here by my colleague, Dr. James Bryan, who's also with STL. And this morning we're going to talk about looking beyond CDUs, or coolant distribution units. And so we did a talk yesterday, and we're going to do one more talk tomorrow, so a three-part series this week. All of them having, I'm going to say, mildly controversial topics. So as we go along here, feel free to jot down some questions, and I'm going to make sure I save plenty of time at the end so we can get to those. So all right, with that, let's get moving. So real quick, kind of the objectives of this talk at a high level. As processor thermal resistance targets plummet, the CDU is becoming a significant contributor to the temperature drop between the processor and the facility water. I think most people are starting to see that. We see a demand for ever decreasing approach temperatures on CDUs for that very reason. The only way to reduce the temperature drop imposed by a coolant distribution unit is to increase the physical size of the CDU for a given heat load. In other words, to reduce the approach temperature, we must increase the liters per watt of the CDU heat exchanger. I think that stands to reason. And then last bullet point here, in this session we're going to examine the thermodynamic costs of CDUs along with the opportunities and challenges of potentially removing them from the data center heat transfer path. So hopefully that's what you came here to see today. All right, kind of a background on CDU cooling in the data center. So at the end of the day, our goal at STL and what should be anybody's goal at heat transfer research companies is to understand the entire heat transport path from processors to outside air, right? And so those who are familiar with the art of thermal engineering and heat transfer know we typically use an analogy called thermal resistance. It follows just like electrical resistance. Resistors stack or sum when they're in series with one another. And so in order to reduce the overall temperature drop from the far left side of this screen, which would be the junction temperature of a processor, to the far right side of this screen, which is the outside ambient air, we need to look at how we can reduce the individual thermal resistances along that path, right? Theoretically, if somebody were to create a superconductive heat transport path that had zero thermal resistance, you would be able to have a junction temperature that was the same temperature as the outside air. But what's important to remember is that, chiller aside, and I'll talk about that in a moment, the junction temperature, of course, can never be less than the outside ambient air temperature because heat has to transfer from high temperatures to low temperatures. The amount of temperature drop is directly related to the thermal resistance stack, meaning the sum of all of these resistors in series. So today, if we kind of, again, these are bulk parameters made to create a conversation that's simplified that we can have together. If we look from the junction of a processor, we've got the package resistance, so literally the heat transfer resistance from the junction temperature sensor of a die to the lid of that die, where that heat can then be removed via a cold plate or a heat sink. We have the heat sink or cold plate if it's liquid cooled. We have an interface across a heat exchanger, in this case probably a liquid to air craw or crack unit, or we have a coolant distribution unit, which is what we're talking about. Potentially go through a chiller. Chillers, unlike the other thermal resistances in the stack, act a little bit more in electrical terms like a transformer. They're able to create a temperature drop or a change in the temperature range, so a little bit different. And the final one is the interface heat exchanger between the cooling water supply, the condenser water supply of that chiller and the outside air. So we want to look at each one of those things individually and see how they overall impact the temperature rise of a junction within a processor. Okay, so this graph, I spent more than 30 seconds thinking about the best way to represent the scenario that our industry is currently in. And I chose to use a piston and a spring. And so right now, everybody is very familiar. I would be the 10 millionth person to note that thermal design power of processors is going up somewhat slightly recently. Most people know that. But what's maybe not known in as much detail is that that is coinciding with a commensurate drop in the allowable case temperature of those CPUs due to a relatively modest change in the junction to case thermal resistance of those processors. And so that causes a compounding challenge for thermal resistance. So T-case, the temperature, the physical temperature of the processor we're trying to cool off is dropping as TDPs are going up. And I'll show kind of what that looks like. So that's pushing down let's call it the allowable facility water supply temperature. On the other side of that vertical stack that I show there is a spring. Again, similarly, most people are aware that facility water supply temperatures, if we increase those temperatures, we can see remarkable returns on energy efficiency improvement in the data center. In general, we want to drive facility water temperatures up as high as we possibly can, because that means that in most climates we're using less mechanical chilling, which is one of the biggest energy offenders in the entire heat transfer stack, and we get higher coefficient of performance out of our cooling towers. So we want FWO temperatures to go up. And the liquid cooling industry, back when we started this, let's call it 15 years ago in earnest, the liquid cooling revolution was supposed to drive facility water supply temperatures up, right? That was the sales pitch. We all made that sales. I helped make that sales pitch. What happened was we also gave a license for thermal design powers to go up, and they did, and they went up so fast that suddenly now we're having conversations about dropping facility water supply temperatures back down below where they were previously, and that's the wrong direction. So let me give a real quick, and I don't want to spend much time on this. By the way, there's way more content here, again, than I have time to go over today, so I'll try and be efficient with everybody's time. But all of the slides that we presented yesterday, today, and tomorrow, we're going to put those up online. So if we didn't get to every detail here, they're going to be online along with any sources, and we want to obviously encourage a conversation. So please reach out if you have questions along the way. So this curve over here, it shows kind of the let's call it a common package structure, right? Just in simplified terms. We have a junction temperature at the bottom of a die. We have a TEM1, which is the TEM material between the silicon and an integrated heat spreader or copper plate. And that's typically where we'd measure the case temperature at, the physical temperature on the outside of the package. And what's happened is junction to case thermal resistances over the past 15 years have improved, but not at the same rate that thermal design power has gone up. And so as processor thermal design power has gone up, maximum case temperature is going down pretty rapidly, right? So when I started my career in 2009, it wasn't uncommon to have Xeon CPUs with case temperature limits in the mid 80 degrees Celsius range. Now we see them in the low 50 degrees Celsius range and falling from there for certain future SKUs. It's because the junction to case thermal resistance is not getting much better. Now, when you actually look at the generation over generation increase in thermal design power, most people can pretty easily do the math in their head. Well, we have a 500 watt TDP CPU today. We had a 250 watt TDP CPU last year. We've got a 2x increase generation over generation for TDP. And it's accelerating faster than that. But the part that's maybe not as well understood is that when you couple that with a decrease in case temperature, the relative cooling difficulty, just being the ratio of thermal resistance requirement of this generation versus last generation, is going up exponentially. So in some cases, a 1,000 watt processor is not just 2 times harder to cool than a 500 watt processor, right? It's like 10 times harder to cool than a 500 watt processor because of that commensurate drop in T case. So, anyways, so let me go back to my screen here. So that part in the middle between the spring and the piston that I have at the top, that's the thermal resistance between the case of a processor or the lid in a lidless GPU and the facility water supply. That seems to be the part that everybody is focusing on right now. There are dozens of liquid cooling solution providers just like us who are trying to solve that problem. So let's look at that problem a little more closely. So this is that same thermal resistance stack broken up a little bit to show the individual contributors. And so obviously we've already talked about the junction to case thermal resistance, and it turns out when you lay this out for a 500 watt TDP CPU, that's a huge chunk of the overall budget that I have for temperature drop from junction to facility water supply. So let's not kid ourselves. That has to be addressed, but that's being addressed by silicon providers, not by liquid cooling solution providers. The next chunk, the one that I over here, owned by cooling provider, that's from the external surface of that die, whether it's a copper heat spreader or it's the top lid of the silicon, to the facility water supply. We go through a TEM, a thermal interface material, we call TEM2 because there was a TEM1 previously, it's the second TEM. Then we're going to go through a cold plate and then through a coolant distribution unit. TEM, still not a huge contributor on current generation of CPUs, right? Maybe 1.5 degrees Celsius drop across the TEMs. The cold plate, 5 to 15 degrees Celsius is pretty common. Most people are trying to design their cold plates for a 10 degrees Celsius rise or less. That's kind of right in the middle of the range that we're seeing here. But that next one is the CDU. And the temperature I show there, 3 to 15 degrees Celsius, that's the approach temperature of the CDU. So approach temperature of the CDU, simplest terms, is the temperature drop between the water that comes out of the CDU to go to a cold plate to cool off the processor and the temperature of the water supplied by the building, right? And obviously we want to get those as close together as we possibly can, but I previously mentioned on our first slides, the only way to do that is to make your CDU extraordinarily large. There is a practical limitation on how big a CDU can be in a rack. It has costs, both capital expenses and in space that coincide with that. Also, making your CDU extraordinarily massive is somewhat antagonistic towards the densification process that most people have been trying to achieve for the last decade or so. What you should take away from this is that the 3 to 15 degrees Celsius range I show on the page here, which aligns with ASHRAE's TC 9.9, liquid cooling guidelines, average CDU approach temperature. So that's just kind of, I'm going to say, a general field for all CDU vendors today. Most are not approaching 3 degrees Celsius. Most are not as bad as 15 degrees Celsius. I would say that many of them wind up right in the middle of this, right? So maybe in that 7 to 10 degrees Celsius range on average. What you see there, though, is when I look at this stack, suddenly the path between the case of the processor and the facility water supply, maybe half of that is the CDU, right? So we have a tremendous amount of effort going into liquid cooling solution providers, cold plates with single-phase water, with two-phase refrigerants. At the end of the day, we're all trying to solve the cold plate problem for the most part. The CDU problem is becoming the biggest part of the overall thermal resistance stack. So as I mentioned previously, the approach temperature, right, that 3 to 15 degrees Celsius range, it depends upon heat load, and it also depends upon the physical size of the heat exchanger. So you can drive down the approach temperature by having a lower heat load. Who's doing that? You could also just make the thing gargantuan. That's an option too. I've got a 0 degree C approach temperature CDU. It operates at 0 watts of heat load, right? I mean, that's great numbers. But anyways, sorry, I get snarky in the morning. Anyway, so hopefully that part's made clear. So if I then go and look at, I'm sorry, this is the wrong slide, and I did it again. All right. I'm sorry, guys. I struggle with PowerPoint. This is a problem yesterday. Okay, so going back then to this view of kind of the entire data center liquid cooling heat transport map, and still using our same analogy for thermal resistances. I'm looking at the processor on the far left over here, going through a cold plate, going through a CDU, but then I show the rest of the network, right? So I might have to go through a chiller, depending upon the climate, the time of year, and then go through a dry tower, or I might have an economizer that allows me to bypass mechanical cooling for some portion of the year or some portion of my heat load, and possibly going through an evaporative cooling tower. What's important to note, however, that each one of these thermal resistances, they matter, and the larger the temperature gradient across the resistor, the more heat that will flow through that resistor. That's just heat transfer 101. And so if I can put a higher temperature on, let's say, this TCWS, if it's hard to see, that's the condenser water supply. As that temperature goes up relative to the outside air temperature, I can transfer more heat through that cooling tower, or I can transfer the same amount of heat at much less energy cost to do so. So this graph over here, this is a dry tower cooling efficiency versus temperature rise. As I increase the delta T between the cooling water supply, the chilled water supply, and the outside dry bulb temperature, the coefficient of performance, which is just the ratio of the heat removal divided by the amount of energy it cost me to remove that heat. So in the case of a dry tower, you're literally talking about pumps and fans. I get significant return in coefficient of performance and improvements, right? So I can drive my CWS temperature up, I can drive my COP temperature up. Well, now let's look at the relative impact of the CDU in the grand scheme of COP at a cooling tower level. If I have a 3 degrees Celsius approach temperature, I go from a 2 to a 5 degrees Celsius swing on the relative temperature of CWS to outside air temperature. my COP almost doubles during that reign. Chillers are even worse. It's happening again. Tomorrow I'll have somebody else work PowerPoint. Chillers have the same problem associated with them, right? The COP of a chiller depends heavily upon the temperature gradient across it that you're trying to achieve. So the point of this all being that when you actually look at CDU's impact on the entire data center, of course there's the temperature gradient between the facility water supply and the case that we're trying to solve, and the CDU might be half of that. But what's maybe worse is that causes a temperature drop requirement on the facility water supply. The facility water supply temperature dropping down means the chiller has to operate more hours per year, and that means that the coefficient of performance of your dry tower is going down as well. So it actually extrapolates out to be a fairly significant impact on overall data center energy consumption. This was water chiller. So you guys come back to this, look at it later. Nice COP versus delta T on the chiller. All right, we're in the wrong place. Who works PowerPoint, honestly? Okay, so this is kind of the thesis all boiled into one slide. I'm going to go back a slide. We're not ready for thesis yet. I got a few minutes. CDUs, okay? So cooling distribution units provide a number of wonderful benefits. This is not the anti-CDU campaign. I should have started with this, but at Strategic Thermal Labs, we sell CDUs. So obviously not trying to kill my own market, this just feels like the right thing to do. So when we're trying to drop the overall thermal resistance from our processors to the outside air so we can improve energy efficiency across data centers, this is a stone that needs to be kicked over. I believe that as a guy who wants to sell you a CDU. So just putting that out there. CDUs, many positive benefits. Condensation prevention, coolant loop isolation for harsh water chemistries that might be present in facility water supply. They give you a control and monitoring point for your liquid cooling system health. All those things are great, and a host of other benefits. So don't get me wrong, CDUs are valuable in the data center space, and not everybody is ready for a non-CDU world. But we can't ignore the thermodynamic efficiency loss imposed by the CDU. At best, it's a thermodynamic parasite in the overall system of removing heat from processors and sending it to the outside air. That's the way that I view it. I think many people view it as a necessary evil, and in many cases it is a necessary evil. That doesn't mean that we shouldn't try to solve that problem. So I think I've already covered that in fairly good detail. So what about a world where we didn't have CDUs as an example? And so just kind of running this to put some numbers up here. The big win here is that for equivalent facility water supply temperatures, we can remove significantly more heat from a similar package. If we keep all parameters exactly the same, heat removal goes up significantly, in some cases over 100%. The amount of heat that we can remove because we removed the CDU from the loop gets higher as the facility water supply temperatures get closer to the case temperatures of the process that we're trying to cool. That's an important detail to remember. So as case temperatures are plummeting and getting ever closer to facility water supplies temperatures, the response is going to wind up looking like we need to drop facility water supply temperatures. I already see significant calls to reintroduce chilled water, 5 degrees C or 10 degrees Celsius water temperatures to cool off liquid-cooled hardware. And that was kind of, I'm going to say that was one of the bigger reasons to get rid of or to add liquid cooling to data center to begin with, right? We can also send back hotter temperature water with the CDU removed, which is important for building heat reuse and drives up, again, the CDU or the COPs of the back-end infrastructure. Okay, call to action. So just a few fun facts here. CDUs have served a valuable role in the transition towards liquid-cooled data centers. However, they have come to be thought of as an absolute necessity without necessarily considering the cost, and I'm not talking about the dollar cost. Fact, CDUs are a source of thermodynamic inefficiency that is costing data centers to waste energy. That's true. We just talked about it. Fact, as silicon heat dissipation goes up while their allowable temperature go down, cooling solution providers are beginning to explore the use of exotic materials, such as environmentally challenged refrigerants, and move back towards chilled water right? That is in the opposite direction of PUE improvement. You don't add chillers to decrease PUE. You increase PUE when you add chilling. Bullet point 3, the most energy efficient method to cool any electronic device, regardless of what we're talking about, is to eliminate as many thermal resistances between the source and the sink as possible. That is just restating everybody else's thermodynamic laws that we've come to accept. The final one on here is my opinion. At elevated component power, the operational challenges that CDUs help solve for data center liquid cooling are shrinking in comparison to the thermodynamic challenge that CDUs create. Ultimate energy efficiency in the data center looks like facility water supplies being routed directly to the heat source without passing through high-loss intermediary devices. All the operational challenges that CDUs abate are solvable in a non-CDU liquid-cooled environment, and that is where liquid cooling solution providers should be devoting their R&D efforts. So the final thing I will say on that, at Strategic Thermal Labs, we have been researching this for a very long time. I think it's entirely viable. I think that all the benefits that, that CDUs provide are something that we can solve around, and we have. But certainly we don't want to be the only ones doing that. We think that the entire industry should be looking at this pretty heavily. You know, I think that we've gotten to a place where when we compared previous chilled air and chilled water PUEs to modern liquid-cooled data center PUEs, we got really excited and happy about the fact that PUEs were now in the 1.03 or 1.05 PUE range. That doesn't mean we should stop trying. It turns out that the last, 10 to 20% of that small chunk, when you're talking about data centers that are being built out that consume 300 to 400 megawatts of power, those losses imposed by a CDU for a data center that size could literally power small towns. Like it's massive, right? So it's kind of the law of big numbers, but even small percentages of a big giant number are still big numbers. And so that's kind of the point here. All right, I will stop and we can have some questions.
All right, thank you. Any questions? Back here.
Thanks a lot. It's Sam from Corinthus. One question I had was another trend that we see is in cold plates that the feature sizes are often dropping from, say, like 300 microns to 100 microns. Given the increased filtration requirements of smaller feature sizes, do you see any challenges of having the CDU out of the loop and facility water going directly into these, let's say, more sensitive environments? Absolutely. So there, again, feature sizes are dropping because we want surface area. Cold plates are two-dimensional heat transfer devices today, and the best way to get more surface area is to shrink the microchannel hydraulic diameter, right? As small as we could possibly go within the realm of manufacturability. That's very true. However, not the only way to decrease the convective thermal resistance on a cold plate. Lots of other ways. We have our competitors have some other ways. You can make up the difference on surface area through other higher heat transfer coefficient improvement methods. It gets you maybe close to parity with a 50 micron cold plate channel, right? But we just gave you back 7 degrees Celsius, and that winds up being a much bigger net gain in the thermal resistance stack if you start compartmentalizing it that way. The other thing I would point out on that topic is two things. One, obviously, rack filtration is an option. We have a solution for that. So you can filter water as it goes into the cold plates. But more importantly, we should consider how much energy does it require for a data center to maintain high quality water compared to how much energy goes into chilling that water, right? You have this dichotomy where some data centers have got facility water supplies that look like the Hudson and the Mississippi River. I'm sorry for those who don't reference or know the reference. Those are very dirty, muddy rivers in America. Like those two rivers are rushing through your pipes at all times. And that's probably hyperbole. There are other data centers that have spent hundreds of thousands, if not millions of dollars on facility water treatment devices that automatically monitor chemical constituents from the water. They do onboard filtration. They're using biocides. They're actively monitoring cultures growing inside of their algae formation, et cetera. I am of the opinion that that is the direction to go.
All right, next question. In the front here.
So the question was, what's happening to water pressure and flow rates in systems without CDUs, I presume? Yeah, so pressures are obviously going up. So one of the things that CDUs provide is kind of a separation of high pressure facility water supplies, and building water pressures are high because they have long flow paths to push water through, right? And they have a lot of devices on those networks, and so their differential pressure winds up being quite high, and so the facility water pumps can be, operate at 100 psi static pressure in some cases. CDUs, on the other hand, tend to operate at half of that or less, right? So cold plates are being designed for CDU water networks that have maximum static pressures of 50 psi, as an example, right? So if you go in to make a cold plate for a processor that's meant to survive facility water supply, it means designing a cold plate that can survive 150 or 200 psi pressure. That's not difficult to do, right, if you design it that way from the beginning. Just talk to some of the folks who are doing two-phase refrigerant-based cooling. All the refrigerants that are being utilized for that are high-pressure refrigerants. It's quite solvable. Flow rates, conversely, would actually go down. And the reason they go down is because we're able to run a lower temperature water into the cold plate because I didn't lose 10 degrees Celsius going through a CDU, right?
All right, other questions?
I thought there'd be more questions than this.
All right, do we have any questions online? Did you see any there? I didn't see any.
Okay, well, thank you again for attending. We will have these slides up on our website later this week. We just wanted to wait until all the presentations were done. So if you had any other questions or you think of something in the future, please feel free to reach out to us.